substitute it inside the equation, the y-intercept is going to be xd. R is the reflux ratio plus 1. According to this equation, there is RD there. If you look at this equation, there's subscript D. Ignore that subscript D. Just don't worry about that subscript D there. Just ignore it. Yeah, because there's two types of reflux ratio. Just for your information, there's two types of reflux ratio. And let me try to get the diagram. And okay, the diagram is not here. But there's two types of reflux ratio. If you look at this diagram, the reflux ratio that is used by this equation is equal to L. That's the L over D. That's that D, the distillate. There are some reflux ratio that is V. There's another reflux ratio that is L over V. This is the V. Okay? But we're not going to use that reflux ratio. That's because of the two different reflux ratios. Some textbook use this formula RV. Some use this formula RD. So our textbook only use just one reflux ratio, so we don't have to worry about this reflux ratio. We don't have to put the subscript there. It's just capital R for that reflux ratio. So for our y-intercept, that is the y-intercept equation, the equation for the y-intercept. So to calculate that value for our example, where is my graph? There's the graph. That's the y-intercept, the equation for the y-intercept. So all I have to do is substitute the values or plug in the values for my, inside this equation, my composition for the for the distillate, the mole fraction is 0.95. That's given. My reflux ratio is 4 plus 1. That will give me 0.95 divided by 5, and it happened to be 0.19. And that is that value there, 0.19. So with these 2 points, one of it is on the y-axis, which is the y-intercept, and the other point, which is on the 45-degree line, is try to move this side. Okay, there is your your value. That is that value on the 45-degree line. So you connect the 2 points, you will get your enriching operating line. And let me tidy up a bit. This is on the, I want to erase that. Okay. I wanted to erase that. I can't seem to be able to erase it. Okay. So your enriching operating line is this line that connects the point on the 45-degree line and the y-intercept. So that is your enriching operating line. Yes, that's we have done that. So next would be to get the Q line. So if we look at our notes, the Q line, this is the definition of the Q line. Q is the fraction of the feed that is liquid. The fraction of the feed that is liquid. That is the definition of Q. And there's another, to get it, to calculate Q, you use this equation where your latent heat is that of the feed. The CP is the average latent heat of your liquid feed. It should be liquid, okay? And TB, subscript B, is the boiling point of your feed. T subscript F, capital F, is the inlet temperature. The inlet temperature, the feed temperature. So if you substitute the values inside the equation, which we have already done before the break, this is the equation that we use. The equation that we use to calculate Q. And we substitute the values inside the equation. And you manage to get 1.1952. That is your Q, the value of your Q. Yep, that is the value of your Q. And in order to draw your Q line, you have the equation for Q, the Q line equation, which is that equation. So this is your slope. That is your y-intercept. So we have our equation here. When we plug in the values of Q, plug in the values for Q and the fit composition, the mole fraction of your fit is 0.45. So when you plug in these values inside the equation, you got the equation in this form. This is your equation of your Q line. So this is your slope, and that is your y-intercept. Okay, so when you want to draw your Q line, let's look at our graph. We will start at the 45-degree line. You will start at the 45-degree line at the composition of your fit. This is your fit composition. I'm going to get a straight line there. That's your composition of your fit, 0.45. Okay. So on the 45-degree line, you have your first point. The next point, either you use the y-intercept or use the slope. Unfortunately, you can't use the slope or the y-intercept because the y-intercept, the value is negative. That value of y-intercept is negative 2.305, which is beyond our range of our graph. Okay? Your range of your graph is from 0 to 1. So it will be very far below the graph itself. It's too far. So it's not wise to use the y-intercept. So what we're going to do, we're going to use the slope to calculate that. So I'm going to bring this up. We're going to use the slope to calculate your Q line. So that the slope, if you look at the slope is equals to positive 6.123. That's the slope. Negative in front of it, and then the break in front of it, another negative there, so it becomes positive 6.123. And that slope is equals to delta y over delta x. And you know that your first point is 0.45 on the 45-degree line. So you have y minus 0.45. And the other line, the other coordinate for y, it's for x, sorry, is 0.452 because it's on the 45-degree line. That is that line, that point there, yeah, on the 45-degree line. So if you set one of the value, for example, you set the x value, you will definitely need to find the y value. So let's say, we did this last time, let's just put it very close to that 0.45. But if you calculate your y, let's see, what will we get? So 6.123, x is 0.5 minus 0.45. And that will be plus 0.45. See what's the value. Anybody managed to get a value before I got mine? Ouch. I seem to be getting a negative. How could I get negative? I cannot get a negative. 0.5 minus 0.45. That is positive. Cannot be negative. 6. Yeah, that's right. Now I'm getting a positive value. I got 0.756. Anybody getting a different value? Guys? Double check my calculation, please.
Get the same value, doctor.
Okay, good. So now, if you use 0.5, that is 0.5, yeah, and 0.7456, That's 2, 4, roughly 0.575. So it's somewhere around there. So that's how I get that value, roughly. Okay? If you use a proper graph paper, you can easily get that point. But if you're just using, without a proper graph paper, I think that would be very, it's not difficult, it's just that it's not that very accurate. So now you have 2 points, you can draw your Q line. So now you already managed to get our Q line. Okay, so that's our Q line. So the next step of the process, before I go to the next step, I need to point out that there's another method to get to draw your Q line without having to use this equation, without having to use this equation, okay, without having to use the equation for the Q line. There's an easier method, provided that you meet the requirement. Yeah. For this is the drawing for the Q, the different types of Q line that you will encounter. Yeah? When your Q line is equals to 0, when you sorry, not the Q line, when the Q value is equals to 0, your line will be horizontal. You don't really need to get the slope. You don't need to get the y-intercept. You know it's going to be horizontal. When your Q value is equals to 0, your Q line will be horizontal. And when your Q is equals to 1, you will get a vertical Q line. You don't need to calculate the slope again. You don't need to calculate the y-intercept. But if it anywhere, neither is it Q equals to 0, neither is it equals to 1, then you have to calculate the slope. You have to calculate the y-intercept. But obviously, the y-intercept normally is not, unless you get this line here, the line whereby Q is less than 0. If you get that line, I'm getting an arrow there. If you get it, let me use a different color to differentiate what I'm pointing at. Okay. If you get Q is less than 0, then obviously the y-intercept is going to be within your range of the graph, within the range of the graph. And if your Q is between 0 and 1, and if Q is between 0 and 1, obviously your y-intercept is going to be within the range of the graph. But unfortunately, if your Q is greater than 1, the y-intercept is going to be way off the graph. Okay? So that's the case that we encounter here, because our Q that we calculated earlier is greater than 1. Okay? The Q that we got earlier is 1.1952. That is greater than 1. So that's the reason why our y-intercept is very far beyond the graph. So it is not wise to use the y-intercept unless your Q is less than 0 in this case. Let me highlight it in this case. Or when your Q is between 0 and 1, then it is within the range of your graph. Your y-intercept is there or there. Okay? So it depends on what is the value of your Q. And again, I would like to stress the fact that if your Q is equal to 0, you get a horizontal line. And if your Q is equal to 1, you get a vertical line. You don't need to use the equation for the Q line. Okay, so that's why when is Q equals to 1? Q is equals to 1 when your feed is at its boiling point. When the feed is at its boiling point, then your Q is equals to 1 based on the equation for the Q that we could use before, because you have to remember this is the latent heat of the feed, and the boiling point is that temperature, and this is equals to the same boiling point. So this will become 1 minus 1 equals, the same value, this is equals to TB, and that will become 0, isn't it? So the whole thing becomes 0. You end up with Q equals to 1. So that's when your boiling point, your feed is at its boiling point, then Q equals to 1. When Q equals to 1, you have a vertical line for your Q line. And when is it equals to 0? When you have a saturated vapor and it is completely vapor, then your Q is equal to 0. For the rest, your Q line is greater than 1, that means you have a cold feed. For our example here, our Q is greater, the boiling point of our feed, the boiling point of our feed. We have calculated it before this. Let me try to show you guys how it moves. That equation is now moved. Where is the boiling point of the feed? This is the boiling point of the feed. That's the boiling point of your feed. Yeah. But the feed itself, if you change the boiling point into Kelvin, 94 degrees C plus 273, that value is 367. That's the boiling point of your feed. Whereas the feed itself is 327.6. That means the feed is, the boiling point of your, the temperature of your feed is lower than the boiling point. So your feed is actually a cold feed. That's your feed. That's your feed. Your feed is cold feed, because the boiling point is higher than the temperature of the feed. So your feed is actually a cold feed. That's the reason why your Q is greater than 1. And when your Q is less than 0, that means you have a superheated vapor. And when it's between 0 and 1, that means you have a mixture of liquid and vapor as your feed. Your feed is a mixture comprising of liquid plus vapor. So these are the 5 conditions that you will encounter. And depending on the condition, you can easily get the Q line. You can easily draw the Q line. Okay, the next step, we have already got the Q line. The next step would be to get the stripping line, the stripping enriching operating line. The stripping operating line it can be done by connecting the point on the 45-degree line at the composition of XW, which is the bottom product, the mole fraction of the bottom product, with the intersection of the Q line and the enriching operating line. The intersection, where is the intersection? Let's look at our graph. The intersection is here. Okay, that's the intersection of your Q line and the enriching line. The other point is on the value of XW, but on the 45-degree line. So if we extend that, that will be there. That's the value. That's the point, sorry, that's the location. That's the point at the mole fraction of XW on the 45-degree line. So that's the point that you're going to use to connect to get your stripping operating line. So you have one point on the 45-degree line. The other point is the intersection of the Q line with the enriching operating line. So with these 2 points, you have enough to draw yourself a straight line. So I'm going to draw myself a straight line. That's my line. I need to get it. It's too fine. Let me. That's too big. Okay. Okay, there you go. So now you have enough lines to get your stages. The next step will be to do the stepping. That means the stages. Okay, this is the part that is the easiest. You have enough lines to do the stages. So you start from the top of the graph, starting from XD. Starting from XD, draw your steps horizontally and vertically, stopping on the enriching line. Okay, that's I better undo that. It is too thick. Yes, you stop on the enriching line, and you continue to do your stages until you meet with the Q line, the intersection of the operating lines and the Q line. If you meet that intersection, you will not continue on the enriching line. You do not stop there. You do not continue your steps until, you will continue the stepping to get the stages, but you will proceed now to go to the enriching line. You do not stop on the, sorry, let me get it right first. This is your enriching line. Let me get this, let me make it very clear. This is your stripping line. So now I'm going to erase this. I'm going to use a different color line. Let me use, okay, wait. You do not stop here on your enriching line. Once you have passed the intersection of the operating lines, you do not stop on the enriching line. You proceed to go to the stripping line. And then you continue the rest of the stages on the stripping line. Yeah. So in this case, I have 1, 2, 3, 4. It's not really completely 4 stages. It's about 3 point, if I extend this roughly, let's see. That's about 3.7 or 3.6 stages. So theoretically, the number of stages or the tray that I will get, I need for this separation for the graph here is about 3.6 or 3.7 theoretical stages. So that's what that's how you get your number of theoretical stages. So we're going to do the same thing for our example. Okay, so I'm going to enlarge this because I need to draw it. Seem to be able to do that. That's my first horizontal line. Stop when it reaches the enriching line. That's my first stage. Next, go to the equilibrium line. Make sure your lines are horizontal and vertical, because I noticed based on the first test, there are some students that is just drawing it without any ruler. I think that's come on guys, you know you're supposed to do it properly. So doing it without a ruler is just not the right way to do it. So this is your second stage. Unless you are doing it, you know, digitally like this, you know it's going to be a straight line because you have your graph paper there. Then you don't need a ruler. But if you have a graph paper that you have to draw manually, then you really need a ruler. Now, I will continue to go towards the enriching line, not the stripping, enriching line, because I haven't yet crossed the intersection. So I will continue to proceed. Okay, now you realize that now I have already surpassed the intersection point of the lines, of the Q lines with the operating lines. So now I will drop my vertical line to the stripping line, not to the enriching line. Okay, I will drop it to the enriching line, not to the I will drop it to the stripping line, not to the enriching line. I do not stop on the first line earlier. Now I go towards the stripping line. So now I will continue to do the same until I reach XW. Next, I will do my stages. Just have to make sure that my line is really straight. That is not straight. I'm not getting a straight line. Okay, there you go. I will drop it to the stripping line. I will not stop on the enriching. I will continue on until I reach XW. Okay, guys. It so happened that it is exactly on the value of 0.1. So now let's count our number of stages. That's my first stage, my first tray, 2, 3, 4, 5, 6, 7. Theoretically, my number of stages is 7 stages. And where is my feed tray? My feed tray is the steps or the stage where I start to shift from the enriching line to my stripping line. So let's write where is my stripping line. This is my stripping line. And which tray is my feed? That tray is my feed tray. Why? Because that is where I shifted from my enriching operating line to my stripping line. So that is my feed tray. So my number of theoretical stages is equals to 7 stages. That is theoretical value. So depending on what is my tray efficiency, then I will be able to calculate my actual number of stages. So that is how you get your number of theoretical stages graphically using MATLAB method. Any questions? Let's look at the solution of the textbook. How many stages do they get? Wow, they get 7.6 stages. 7.6. Somehow I managed to get, I think I must have, I think I got 7. Yeah, I got 7. Somehow I got 7. Yeah. So the last stage, sorry guys, I got to point out one more fact that that is stages, but the number of theoretical tray is equals to 6 trays. Why? Because the last stage is going to be your reboiler. The last stage, the complete stage for the last one is your reboiler. So normally what you will write it is 7 minus 1 equals to 6 trays plus 1 reboiler. Okay, that's how you normally write your number of stages. You have 6 trays plus 1 reboiler. So the last stage should be for the reboiler because your reboiler is a partial reboiler. And if you look at the diagram, your reboiler is partial reboiler. So this partial reboiler will be one stage because the composition it gives an equilibrium. The separation is equilibrium there because this is your this is your vapor. This is your vapor and this is your liquid. So the vapor and the liquid is in equilibrium. So that partial reboiler is considered as one stage. So that's how you write your number of stages. 7 stages, but one of it is going to be for your reboiler. So any questions? Any questions? No? No questions? Okay, again, I would like to point out you shifted the steps once you reach the intersection points. Where is your intersection point? This is your intersection point. So you will start to shift your steps. Instead of going to the enriching operating line, you go to the stripping operating line. So that is your feed tray. Your feed tray is the stage where you change from your enriching line to the stripping line. So that's example 11.74. So now you already know your number of theoretical tray. The question asked for tray is tray. So your number of theoretical tray based on my graph is only 6. That's 1 reboiler. So you need to write the whole thing plus the reboiler. It should be written as such plus the reboiler. So let's proceed with our lecture. That's finish to get the theoretical stages. The same explanation is over here. Okay. This is the example that we just did. The author, well, the diagram that I got here, I got 8 stages. It depends on how you draw your vertical horizontal line. For this diagram here, I got 8 stages. So it just depends, and the feed tray is number 5. For the example that I did just now, I got feed tray is number 4. So it depends on your diagram. Yeah. But it should not be too far off. Now, let's look at when the reflux is total reflux and when the reflux is minimum. Total reflux means, if you look at the diagram, over here you have the top of the tower. This is your vapor coming out, and it will go into your condenser. And if you have a total reflux, that means all of your vapor is going to be condensed. All of it will be condensed, and all of it will enter the column back. All of it will be put or will be returned to the column. None of your product will be coming out as distillate. So that is what total reflux is all about, where the whole vapor will be condensed and returned back to the column. So when it is a total reflux, you will have your minimum number of stages. The minimum number of stages occur when the reflux ratio is equal to infinity, total reflux. And that happens when your operating lines coincide with the 45-degree line. That means you don't have any more operating lines. You don't have Q lines, you don't have stripping line, you don't have enriching lines. You just have the 45-degree line. So how to draw the stages? You start again with from the 45-degree line. From the 45-degree line at the composition of XD. That is your first starting point, and you do the stages until you reach XW. Okay, so in this case, the number of stages is roughly 3.8. So the number of minimum stages for this diagram is about 3.8 stages. Or what you can do is you can use the Fensky equation. You can calculate it analytically, provided, of course, you have a total condenser, because all of your vapor will be condensed. So that means you have a total condenser. So if you use this Fensky equation, you need this value, the average relative volatility. The mole fraction obviously is already given. The XD should be given. The XW should be given. Okay, that's the mole fraction of your bottom product. This is the mole fraction of your distillate. But your average relative volatility, you need to calculate it using this equation, whereby the relative volatility at the top of the column, and this is at the bottom of the column. So you need to calculate your relative volatility, and we already mentioned how to calculate relative volatility. You just need to scroll up to the very beginning of the notes, and you will find the equation to calculate the relative volatility. So if you do if you use Fensky equation, that is going to give you approximately the same value if you do it graphically. So that's how you get your minimum number of stages. And when the reflux ratio is minimum, that happens when you have infinite number of stages. That means you're definitely not going to get any, the number of stages is going to be infinity. Why? Because you look at this diagram, you're going to proceed to draw your horizontal vertical line, you're stepping off until infinity. You will never be able to stop. And that is when you have infinite number of stages or trade, when your reflux ratio is minimum. Okay. So how to calculate your minimum reflux ratio? You have two ways of doing it. Either you use your slope or you use the y-intercept. This is the example just now that we did for the previous example. So ignore this value. That is the equation for the y-intercept. Okay. So it depends on you can use either one of them. You can use slope or y-intercept. I personally prefer the y-intercept. And your graph, how to get your y-intercept. Okay, it depends on the shape of your graph, the shape of your equilibrium curve. If your curve is in this form, where it has an inflection, then your operating line, let me get a different color. Your operating line for the enriching line is started on the 45-degree line at the XD mole fraction. And you should be drawing a straight line tangent to your equilibrium curve. Tangent, it should be tangent. So this operating line should be tangent to your equilibrium curve, and y-intercept is going to be there. So whatever value you get there, you put it inside your equation, then you should be able to get what is your R mean. Whatever value you get from your y-intercept, you should be able to use that value, whatever that value is, to calculate your R mean, the minimum reflux ratio. But if your graph is in this form, where it is an ideal solution, then in order to draw your line, as we have looked at the previous example, you start from a 45-degree line at this composition. You just draw where your operating line, you draw your operating line where it intersects with the Q line and with the equilibrium curve. That is how you draw this operating line. Your enriching operating line should be drawn from the point on the 45-degree line, that point, to the point of intersection. This is your first point, the point of intersection between the Q line and the equilibrium curve. That is the other point. So that's how you draw it. And you will get your y-intercept there. And there's two methods of doing it. You get your intercept there. And if you have your curve is in this format, if your curve, equilibrium curve is in that way, so your first point again is on the 45-degree line, and the other point will be tangent to the curve. Your line should be tangent to the curve, which is the pinch point. So you will get your straight line, and that is your y-intercept. So that's how you get your R mean, by putting in the value of your y-intercept into this equation. Sorry, let me tidy up. By putting the value of your y-intercept into this equation, you'll be able to solve for R mean. Okay, now let's look at our example just now. Okay, I'm going to need going to draw another line to get my R mean. So I'm going to use this a different color so that we will not be confused. So let's use dark blue. My starting point is on the 45-degree line. My intersection of my Q line with my equilibrium curve is that point there. That is my intersection of my Q line with my equilibrium curve. My other point is on the 45-degree line. Since the curve is a perfect curve, that means your system is an ideal mixture. So I will start from my 45-degree line, get to my point of intersection, and I will proceed until I intersect the Q line. Okay. So now my my y-intercept will be 0.45 roughly, or 46. That will be, that's 2, 4, that's 5, not 6 obviously. It's about 4, 5, well, 0.4. Okay, just roughly give it 0.45, just roughly. So that is my y-intercept. So my R mean, if I use the equation just now, let me try to get this. So this is the equation, my R mean equation. So if I use that equation, XD, I'm looking at the y-intercept, XD R mean plus 1. So my XD for this example is 0.95. 0.95. My R mean is the unknown. My minimum reflux ratio plus 1. And from the graphical solution that I just got from my y-intercept is 0.45. From the graph 0.45, I should be able to calculate my R mean. Let's do it step by step. Let's get that value. In my R min, that's my R min. So that's the value of your minimum reflux ratio. And normally the distillation column will operate between 1.3 to 1.5 times the R min value. So that your R min, let's check what is the answer in the textbook. The textbook gave a value of 1.17. That's not too far off, 1.17, and what we got is 1.111. So that's about the same. And next, how to get the minimum number of stages, N min. Okay, if we look at our notes, how to get the N min, the minimum number of stages is just to draw the steps without any operating line. So this is a bit messy if I do it using that this graph. So I'm going to get another graph. Where is my other graph? This is the graph. I'm going to copy it. That's my graph. Next, what I have to do is get my XW and my XD and XF. My XW is going to be 0.1. That's my XW. My XD, 0.95. That's my XD, the mole fraction of my distillate. This is my XW. My XF, it doesn't matter where is my XF, but I just put it here. That's my XF. Because I don't need to get a Q line anymore. I just need my 45-degree line. And that's my 45-degree line. So I will start from XD, my XD, and I will stop at XW. So let's do it using a different color. I will do the stages. We'll continue to do the stages until you reach XW. A good one there. I need to undo that. Just I need to hurry up because it's almost time. Let's just proceed. Okay, not doing a good job here. Let me try to get that. I'm trying. Let's try to get it. Yeah. Okay, so I'm struggling in here. But you get the idea that you're supposed to do the steps until you reach the end, the XW line. That's not a good line. Oh my God. Well, roughly, how many stages? 1, 2, 3, 4, 5. It's about 5.6 maybe. So my minimum number of stages is 5.6. So N mean it's about 5.6 stages. Let's look at the solution in the textbook. What the textbook got? 5.8. Okay, that's not far. That's about the same. We got 5.6. The textbook managed to get 5.8. So that's how you get the minimum result ratio and how you get the minimum number of stages. Any questions? Any questions? I hope you managed to get to understand the how to cooperate, because your second test will be tested on this using my CAPTIL method. So we will be looking at more special cases of McCaptil. Beside the example that we have looked at, we also have stripping column. We have stripping column. We have enriching column, and direct steam injection, and the last one, side stream. Okay, this is another example, another special case, partial condenser. So that will be just looking at tray efficiency. So depending on the tray efficiency, you can get the actual number of stages. So if there's no questions, we will stop here. Okay? So we will be looking at most cases of McCaptil during the next 2 hours. And by then, we should after that, we'll be looking at we should be looking at the multi-distillation, but I'm thinking of not doing it immediately after McCaptil, because multi-component distillation will be covered in the final. So I'm kind of thinking. I would prefer to do it towards the end of the semester, the multi-component distillation, so that you have it fresh before the final, because it will not be covered in the second test. So might as well we proceed with the liquid extraction, which will be covered in the second test. Okay, guys. If there's anything else, we will stop here, unless somebody have a question to ask. Anybody? Oh, okay. I'm looking at the chat. Okay, there's no questions. Okay, guys. Thank you very much for your time. And we will be looking at, we will meet each other again on Thursday. Assalamualaikum warahmatullahi wabarakatuh. Welcome, guys.
Thank you, Doctor.